Super. Okay. Thank you. It's a pleasure to be here. Thanks to Diego and the other people for starting this initiative. I think it's super exciting. Thanks to all of you for coming. When Diego asked me to do this, I kind of had this imagined meeting where it was Diego, a few of his buddies, we're in a room, there's a whiteboard, I'm just going to show up and kind of talk a little. And then maybe it was 2-3 weeks ago, Diego said, great news, Rob. We have about 75 people registered. We need your title and abstract, and then there's going to be a reception. I'm like, whoa, all of a sudden this is a big deal. So he put the pressure on, so I hope I deliver. I wasn't sure, I figured there's maybe a broad audience here, so I'm going to try to tell my story with mostly pictures and not too many equations. And I'm going to try to connect some of the things you may be familiar with things you're less familiar with, and tell you what we know and understand and what we don't know and understand yet, and some cautionary notes and open problems at the end. Okay, so what is machine learning? This is the way I always start off. So if this is too much in a baby spirit, just bear with me because I think it's important we're all on the same page. So machine learning is basically writing computer programs that learn from data or examples like children learn about the world around them. And the hope is we take all this raw data, we plug it into a machine, and it kind of sorts out and finds important information for us, features and so forth. So here's my little example that I always start with. It's Dora the Explorer. She's going to learn how to tell the difference between different types of fruits, apples and oranges. So what would Dora do? She would start extracting features from these images. She'd look at the colors and she'd look at the textures. And then based on those colors and textures, she could develop a discriminatory rule between apples and oranges. So we'd tell her this is an orange, this is an apple. She'd see oranges are orangey and wrinkly. Apples tend to be red or at least smooth and shiny. And so that's how she would learn. Machines kind of do the same thing. They don't have eyes. We have a camera. They can extract visual features too, like texture measurements and color measurements. And then we can tell the machine what's an apple and what's an orange just by saying apples are +1s. Ooh, that came out weird. Sorry, there may be some problems with the conversions here, but hopefully you get the point. Oranges are -1, apples are +1, so there's just a binary table of data in there for the computer along with the coordinates in this feature space, and it just learns a classification rule, this decision boundary. So essentially the same thing that Dora is doing. And this little rule is just it's a line, so we basically have to have two weights for the slope and intercept of that line. We weight the two features accordingly. We look at the sign. If you're on one side of the line, it's an apple. If you're on the other side, it's an orange. So that is Machine Learning 101, and at some level, that's all we're doing throughout all of these things that you may have heard about in the popular press or seen about here in the medical school. Okay, so let me just give you one quick example of something I've done. I'm not going to talk too much about work I've done, but I just thought I'd flash one thing up, which is essentially an extension of this very simple idea that I just showed you. And let me just also say right here, if anybody has a question at any point, just feel free to raise your hand. We can take questions on the fly. So the idea is that you're going to put a person into a fMRI scanner. They're going to be getting some visual stimulus while they're in there. The stimulus will be in one of two types. I'll show you that in a minute. So one class of stimuli, another class of stimuli, and then we're going to try to predict based on their time series coming out of their pixels or voxels what they were looking at while they were in the scanner. So we want to basically read their mind using fMRI, and all we're going to do is the same thing. We're going to take our features, in this case are going to be the pixels or the voxel data that we record. We're going to have to choose some weights to figure out which voxels are important, which ones are encoding that information, then just take the sign of that weighted combination as our prediction. So here's how it looks. The visual stimulus in this kind of experiment that I'm talking about are of two types, either a sentence of a concept or a visual image of the same concept. Okay, so we'll encode sentences are going to be +1s, and the visual representation is going to be a -1. Now we're going to put the person in the scanner. They're going to see different sentence or visual representations of that same concept, and then we're going to try to predict, are they reading a sentence or seeing a pattern? Which one is it? So there's a kind of a higher level cognitive process that we want to figure out where it's happening in the brain. So we basically just have a time series. That's the stimulus pattern. Was it a +1? Was it a -1? What were they seeing at each point in time while they're in the scanner? we're also, ooh, that really that's supposed to be a pixelated version of their brain. And in each of those is supposed to be the time series of the voxels in each location in the brain. We're going to take a weighted combination of those voxel time series and then try to predict the time series of that label sequence. Okay? So it's exactly what we were doing before. That's the picture of it. And importantly, what we want to do, and I hope this shows up over here, yeah, we want to find a solution that has only a few non-zero weights. Why? Well, our hypothesis is that this decision-making process, or the process that's involving whether they're reading a sentence or seeing symbols, is happening not everywhere in the brain, but in some localized regions. We'd like to discover where this processing is taking place. And so by trying to encourage a solution where many of those weights, the red W1, W2, et cetera, are close to 0 or 0, and only a few that have big weights will say, oh, well, that must be where things are happening in the brain. And so this is the kind of thing people do. These are some cross sections with some students who've worked with us on this. You can see different regions of the brain are maybe encoding different information, whether it's a picture or sentence. These kinds of things are pretty robust and do predict well what the person's seeing. So I'm not going to say more about that, but it's just an example where you take that simple apples and oranges thing and apply it to fMRI. Any questions so far? Great. Okay, so here I looked, I said, well, where is machine learning used in medical imaging? And I found this paper, I guess it's pretty recent, yeah, 2017. It was nice. They said they had a whole survey of all sorts of stuff. So here's a picture from their paper with a number of different applications, segmentation, classification, detection, et cetera, et cetera, et cetera. So you get the idea. I think everybody here knows that machine learning, statistical methods, and so forth are used a lot in medical imaging. Okay, so now I just want to make the connection to neural networks because people hear a lot about neural networks. And the thing to know is that neural networks are, at the starting point, just exactly what I've been telling you already. So remember, what we do in that apples and oranges problem is take a weighted combination of the color and texture. That defines a line, and then we look which side of the line you're on by taking that sign. And so what this looks like if you wanted to draw a little block diagram is you have two inputs. You sum them up with some weights, and then you take the sign, which is that little nonlinearity, and that spits out y hat. That's your predicted label, +1 or -1. So that's a single layer neural network, right? We have some linear combination of inputs, then we take a nonlinear transformation of that, and that gives us our output prediction. So we've come a ways from there. This is what a kind of state-of-the-art neural network might look like now. This is the Google's version of a deep neural network. They can do really fantastic things like recognize fruits, but also cats and TVs and all sorts of other things. What's going on here, it's hard to kind of see, but I want to just tell you that each of those little blue boxes is just one of those things I just showed you. Just one of those little apple and oranges detectors, except we're cascading these all together and tuning up all the weights across all those layers. And somehow, remarkably and somewhat magically, we don't understand quite yet how this is actually working. They can do these great things. Now, I actually did my master's thesis, dissertation, whatever it's called, on neural networks. That was during the first wave of neural network excitement, around 1990 or so. And what's changed since then? Why are we seeing? So in fact, everything was exactly the same. Nothing much has changed in terms of this, except they've made them bigger and so forth. But we haven't really, there's been no big breakthrough in like, oh, we didn't know what we were doing there, and now we know what we're doing now. It's not like that. What's changed is this. When I was doing it, my computer was very slow. Now they're thousands of times faster. The training set I had consisted of a few hundred images. And here's where we are today. So the computers are way faster, thousands of times faster. To do this, they trained this neural network on about 14 million labeled images. So several orders of magnitude more training data also went into that process. And those are really probably the two biggest drivers. And then a lot of good engineering has come along when people got the capability, the large data sets because of the internet. That's why, right? If the internet didn't exist, we wouldn't have large labeled data sets. They actually gamified that whole process to get that large ImageNet database. So lots of data, really fast computers, and then a lot of engineering to get to this point. Okay? But the building blocks are exactly that simple Dora the Explorer thing. Okay, so here are headlines. Everybody's heard these headlines. Computers recognize images, they translate text, they beat us at every game. That's fantastic, except, as I just mentioned, millions of labeled images were needed, probably thousands of human hours gone into curating that training data set. In the case of text, these machines are being trained on more text than a human can see in a lifetime. So a human translator starts off not being able to even speak or read. And by the time they're in their 20s, they're an expert translator. And they haven't seen a fraction of what the machines are seeing. So something's very different the way we learn, the way these machines learn, just a point to make. And then in game playing, these machines are playing so many games, way more games than even my teenage son can stomach to do it. So he can learn to play these games. Maybe he'll still get beat by the machine, but he learns very quickly. Machines learn very slowly. So that has caused some people, including myself, to just say, well, maybe we can train machines with less labeled data and less human supervision. That's one of the areas that I work in. I'll maybe touch on that a little bit later, how people are trying to address that. But that's an important area of research that we and others are working on. Okay, so here is the basic machine learning pipeline. You have raw unlabeled data. You take a random subset of that raw unlabeled data. You ask an expert to label it. She labels it. Now you have a training set. The machine learns a predictive algorithm, one of these linear classifiers or a deep neural network. Take your pick. So the machine automatically learns to label new data based on her training examples. So here's how it looks. I think this is Fang's work, right? So I looked at what did they do here. So they have these MRI images, I think these are, right? And they want to segment them. So somebody goes in and hand segments a few of them. Then they turn it over to a neural network that takes that training data and learns to automatically segment these images. Do I have that right? Rick, you know this. This is correct. Good. Don't want to misrepresent it all. So it's working really well. And it does take some human effort, though. You know, some experts have to sit down and train the thing, essentially. But at any rate, it's working great. And this is a fantastic example of successes of deep neural networks in medical imaging, and I guess we're going to hear more about this in the next lecture. Here's another example, also going on here at campus. This is Peggy Pezic and David Page and some other people taking unlabeled electronic health records, having expert clinicians go in and label them. This person does have this disease, or this person is likely to develop this disease based on what I see in their electronic health record. Then we take those labeled electronic health records, turn them over to a machine, and then the machine can label all the others in the database. That's the goal there. And then you could use all these labeled electronic health records for some genome-wide association study or whatever you want. So there's lots of great reasons for doing this. And then I talked about the fMRI example. Here, there's not nearly a human labeling things, but there's human support and both in acquiring the data and generating the data and so forth, but it's basically following a similar pipeline. Okay, so now I'm going to transition. So what is important to know about machine learning? Machine learning, even a linear classifier, will work fantastic if you have good features going into the input of that linear classifier. So features are the key to effective machine learning. What does that mean? Let me show you. So here is the idea. I'm just going to strip away everything else. We just have labeled training data now. We put it into the machine learning algorithm. It puts out a classifier or a predictive model, a segmenter or whatever. That input is training data. I'll represent it like that, where X's are sort of those features like color and texture, and the Y's are the labels. And so in the context of these applications I was just mentioning, in fMRI, the features are the time series for the different voxels. That's a feature. Each voxel gives you a feature there. The labels are +1 sentence, -1 picture. In the MRI segmentation, they're using some deep learning features. I'll just kind of represent them there. I'll say more about that later, but they're basically visual patterns or features that are going into the decision-making process. And then the labeling here is 0 background, 1 femur, 2 tibia, and 3 patella. Okay, so it's not always just binary, but I'm going to focus on the 2 label binary case just because it's easier to talk about, but there's no reason it couldn't be 4 different classes or whatever. And then in the EHR, the electronic health records are kind of flattened. Ultimately, usually we just have like a binary, huge binary matrix full of 1s and 0s. You something was indicated or something wasn't indicated, and then based on those binary patterns, we're trying to predict whether or not somebody has a disease. Okay, so does everybody understand what are features and what are labels? Good. So here's what a linear classifier is. So I'm going to use through the rest of the talk red for -1, blue for +1, just so I don't have to keep writing numbers. So those are the colors indicate the two classes. We want to learn a linear classifier. So we can do this as an optimization problem. I'm writing down, this is like one of the few equations I'll have, but basically you try to minimize by choice of weights a combination of a data fitting term, which tries to make the output of your predictor match the labels that you're given in your training data, plus some regularization. And the important thing about this particular optimization, this is what's known as a support vector machine, but it's basically just a fancy name for a linear classifier. And the animation wasn't great, I had it a little better, but it essentially automatically finds this for you. You just plug it in and it finds this. Why is that nice? Well, it kind of looks like the line is separating the two classes. It's doing a little more than that. It's actually maximizing what we call this margin. It's putting it right down the middle, so it's sort of as far away from the data points as it can get and still classify correctly. And why that's useful is if points moved around a little bit, well, things don't change so much. And if I had a lot more data, maybe now these are new examples that come in, by putting it kind of in that sweet spot between the two classes, hopefully I will make good predictions on future cases that I haven't seen so far. And that's what's called generalization. I'll come back and talk about that a little bit, but this idea of maximizing the margin also then connects back to good generalization problems, or properties, I should say, or good predictions on future cases you haven't seen yet in your training set. Does that make sense to everybody? Important takeaway here is that we understand it super well. We know how to do this optimization. We understand all the math. We understand its robustness, its stability, how well it will generalize, how many data we need in order to make this work. Everything is pretty much understood. That's not the case with deep neural networks, and I'll come back to that. Here's just to make sure everybody doesn't think everything's two-dimensional, here's a three-dimensional example. This is why I really want to have my movies, because I did take some time trying to make these movies in MATLAB, but it takes a little while. This one's a little long. My apologies. But basically, I'm showing you can imagine have three different features. It's a similar sort of picture. Two classes, ideally linearly separable. And in a minute, there's that. So I'm putting in now not a line, but a plane that separates those two groups of points in 3 dimensions. So in 1D, a linear classifier is a line. In 2D, it's a plane. And you could imagine, for example, in fMRI, we're using thousands of voxels, so we're in 1,000-dimensional space, but there's some generalization of this hyperplane separator going on there. All right, so here's another picture. So here I just have a 2-dimensional feature space, 2 classes, but you can see that I can't separate these with a line, but I could separate them with a parabola. Okay, so this is a nonlinearly separable problem. And, well, you could say, well, maybe we should just try to not just look at lines, but look at polynomials or parabolas or whatever that you could do. Or you can just add an extra feature. And this is usually the way we think about doing it. So we're going to add an extra feature, which is just a redundant feature. We're going to take x1, and we're going to also add x1 squared. So that's our third dimension here. As this rotates around, you can see that x1 and x1 squared are just deterministically related. They're just the parabola themselves. But as I keep rotating into the x2, x1 squared plane, you see the beauty of this. Now look at that picture. That looks like what we just had before, and I can just come in and linearly separate again. So this idea of lifting to a higher nonlinear representation is very powerful. It's sort of what we do usually in practice. And the idea is you go to some nonlinear representation of the original data points, and then you maybe can just learn a linear classifier there. There are ways to do this. I just gave you an explicit construction. Add some extra nonlinear functions of your original features. We usually don't do that. What we do is, what was done a lot was kernel methods. I won't say what kernel methods are, but they're essentially an implicit way of generating all these nonlinear terms. People have written many books on it. This was what everybody did in machine learning up until about 2010 or 2012, when deep neural networks really started to outperform these methods. There are many reasons. Maybe I can talk afterwards about why maybe neural networks are performing better. But at any rate, here's again what's going on now. Rather than explicitly building nonlinear features or implicitly generating nonlinear features. We're actually just learning nonlinear features from data. That's what deep neural networks are doing. They're sort of saying, can we just learn from lots of examples that x1 squared would have been a good feature to use? Okay. So what are good features and what are bad features? Here's a picture. Two features, feature 1, feature 2. If I just look at feature 1's a good feature. If I project down onto it, I see this nice separation between the data. That's a sign that it's probably a good informative feature. On the other hand, if I project over onto this side, it's just kind of a mess, a jumble. Feature 2 probably isn't very good. So one thing we could try to do is just ignore irrelevant features like this because they're not going to really help us with classification. That's essentially what we're doing in fMRI. We're ignoring all the irrelevant voxels that really aren't correlating at all with that stimulus pattern. And so that's kind of behind the scenes there. Better performance if we just ignore feature 2. Okay, so here are methods for finding good features. Start with many features, everything including the kitchen sink. Just throw in random nonlinear things if you want, and then try to prune them out based on training data to select a small subset of useful features. This is one thing that we do and we understand quite well. This is like the lasso and things like that, if you've heard of that. That's what's going on. Again, that's what we did in fMRI. We initially considered all possible voxels, even though we really don't think most of them will be very useful, but we automatically, using the training data, find that subset of voxels that are really important, and that's not only good for prediction, but ultimately shows us maybe where in the brain things are happening. What else could we do? Well, we could engineer good feature representations from first principles, prior knowledge, etc. A good example of this is an electronic health record. These expert clinicians actually do come up with essentially rules of thumb, which combine certain features. Like if you see this box and this box checked in the EHR, then that's a good sign that the person might have this disease or something. So they come up with rules of thumb and then kind of combine them either by hand or then by training. Maybe they give those good combinations of features to a machine learning algorithm. Kernel methods also fall into this. We design kernels with special properties to reflect prior knowledge. It's a sort of way of engineering good features. And then finally is the learning good features from training data directly. And this is what deep learning is doing, and I'll talk more about this in a bit. Any questions on how you get features? So you either take tons of features and just try to sift down to a good subset, or you handcraft or carefully engineer them. Maybe you use Bayesian methods, whatever, or you just try to say, look, we are not going to do anything here. We're just going to take the data and try to learn from data. And we can do that, especially if we have a lot of data like we do in some of these applications. All right, so I want to focus, because this is kind of what we're more interested in today, is learning features from data. So they call this representation learning, and I'm going to kind of go through the history of it, at least as far as I see it. Okay? So here is the first thing everybody learns about learning representations from data. Should we just look at the original coordinate system or some other coordinate system? That's what principal components is doing. So I think this movie will work. So you see the data are sort of in this kind of elliptical-like set, and I have 3 lines there, the pink, the green, and the red. Those are the principal component vectors. So the pink one, which is the long one, is showing you the dominant axis of variation in that data set. That's principal component analysis. Has been around for a century, I guess. Useful in trying to find good directions to kind of pay attention to. Maybe not so interesting here in 3 dimensions, but if I were in 1,000 dimensions, you might want to first reduce it to a more manageable subset because there's probably not a lot going on in many of those thousands of dimensions. So how does that look in MRI? So here's a cross-section of the brain, and here's how we're going to do PCA. We're going to take little windows of this MRI image, and so that's kind of this, I'm just going to, okay, so that box was supposed to be going around, just looking at all these windows, and then taking all those windows as sort of examples, and then doing principal component analysis on all those little windowed snapshots of this MRI image and probably a bunch of others. And what you'll get are features like these. Those are the PCA features. That's essentially the set of features you get from PCA no matter what images you look at. They basically just give you 2-dimensional Fourier features. So low frequency kind of oscillations, higher frequency oscillations, so on and so forth. Nothing terribly interesting comes out, but these features are still probably other than the raw features, which are just pixels in this case, just pixels with gray values. So if you think about what it would do, let's get these both up here. So if I just tried to classify white matter, gray matter using the pixels, it's kind of a mess, right? There's red and blue all over the place. I can't really separate things too well, but if I look at maybe the PCA features, which at least do some local averaging or something, I might be able to start doing a little bit better. Maybe not perfectly separable, but better than just trying to look at individual pixels and make that question. We have to look at the context, right? And at least PCA would be looking at the local context of pixels. Does that make sense? Does everybody understand this? Again, if you want me to answer a question anytime, please feel free. Okay, so, yes. Yeah.
So that strikes me as basically creating...
Oh, wait, I have to go backwards here. There we go, yeah.
Image basis set, and you're
yeah.
projecting onto this image basis.
Yeah, you could think of it this, so you would now say, and I guess I have, it looks like about, well, whatever. Imagine that I take a little block, and rather than representing that little block as, you know, whatever it is, 32 numbers or 64 numbers, which are the pixels, I'm going to re-represent it in this new coordinate system, and now I'm going to learn that linear classifier or the weights over that, the projections onto those basis functions. The idea being that then, rather than just looking at individual pixels, now I'm sort of looking at local averages. That's essentially what PCA would be doing. Okay. So the next sort of step in evolution, and this has actually occupied a lot of recent work over the past decade or two, is what's called dictionary learning. I'll give you a couple of different ways to think about dictionary learning. So again, don't worry about that math there. Just again, something like data fitting term minus some other regularization term. But what we're going to do now is try to find features so that each image patch can be represented with a very small set of relevant features. So this is sort of the sparse coding idea, if you're familiar with that. But rather than sort of saying we just want a basis, we don't want any old basis. We want a basis where every patch can be represented by just a small number of elements from that basis or dictionary. And so here's one way to look at the distinction. Suppose I had a data set that looked like this. If I did PCA, it would just sort of find these two axes, right? So it's kind of like longer this way and shorter that way. So those are the directions of variation in this data set. Whereas if I did dictionary learning, what will happen is it'll actually try to find those two sort of lines or directions in the data automatically. And you can kind of see that those two directions, the PCA directions, probably aren't very useful for classification in this case, but the dictionary learned features would be much more effective because they're kind of paying attention to the geometry of the data with respect to those patterns of labeling. So that's kind of lucky in this case, but that's the idea. Let me show you another way to think about it. Everybody probably is familiar with k-means clustering. That is dictionary learning. Now you're just going to try, for each cluster, you're just going to try to find one vector, one basis element that represents that cluster. So if I had a picture like this, maybe we'd take these guys as our mean clusters and we'd forget about all the other examples. We'll just say any of the other data points could be approximated well by one of these guys. So k-means is dictionary learning with just a one sparse dictionary requirement. So here is what happens if we do this in the brain. Again, the PCA bases are sort of these Fourier basis functions. The learned dictionary elements are more like little edge detectors. And these little edge detectors can be really good, especially if you're trying to say segment between white matter and gray matter. They'll be sensitive to boundaries where there's contrast changes. They'll do that better than the Fourier basis, the PCA basis. And so if we kind of think, again, this is all just kind of to give you the idea of it. Pixel was a mess. PCA was a little bit better. And maybe with dictionary learning, now we actually start to be able to make a better separation because we're actually representing stuff now in a different way, a different coordinate system, which is even better for separating white matter from gray matter. Okay? So that's sort of something that is quite effective. People have used it a lot in medical imaging and other places. And it's in some ways like a first step towards deep learning. So here's deep learning again. This is the Google version. What's happening here is it's sort of like at the first stage, it's learning things that are really a lot like what you saw in the dictionary learning. Little edge detectors, but also some color text detectors and other things, if you're training on color images, that is. So it's doing basically dictionary learning there. If you go a little deeper, you start to see other things. In this case, it was trained on objects like cars and furniture and things like that. And you can start to see more, maybe eyes too. You start to see some of those patterns emerging. It's a little complicated to actually explain how they get these pictures, but essentially what they're doing is they're looking at some node deep in this neural network and trying to figure out what input would cause that particular output to be as large as possible. So they run that as a little optimization. So you're seeing what some of the nodes in that neural network have as their sort of sweet spot in terms of what input stimulates them the most, and that's how they derive what these features are detecting or sensing. And then at the final level, you get really complicated structures out. I don't know what this looks like, a beehive honeycomb or something, but at any rate, you start to see things that look like natural objects emerging. And so this is sort of the idea that we start off with very simple things like edge detectors, and through this emergent property, using backpropagation to train the weights in these neural networks, we start to learn these more and more complex feature representations. And they are nonlinear. That's because all these things have these nonlinearities baked into them. Okay. In practice, what we do a lot in machine learning is just take some features, say way over here, and then just run a linear classifier on them. That's essentially what the final stage of this is doing anyway. So one way to think about deep neural networks is they're just a way to take training data, learn a good set of nonlinear features, then every time you get a new example that you want to classify, you put it into the input of the neural network, it pops out some really rich set of nonlinear features, and then you run it through a linear classifier. So if you want to think about it that way, you can. It's perfectly fine. It's essentially what's going on. The key thing, though, is this learning process. How does it learn these great features? I'd love to tell you. I mean, I think it's very intuitive, right? I just showed you that looks like, why wouldn't that happen? But why would it happen? You know what? Nobody knows. So it's a little bit troubling. Okay, so here's what it would look like. I couldn't find a brain-trained deep neural network, but I did find one that was trained on cars. So you see edges, and then you see parts of cars, and then you see whole cars. Okay, so that's actually what came out of some convolutional neural network that was trained on cars. So that what I would like you to imagine is what's going on is if I just used pixels, I couldn't classify at all. If I used PCA, I started to do something. Dictionary learned things were a little bit better, but the deep features are really working well. Classes are very well separated, huge margin, very easy classification problem at that stage. Using those deep features, I just come in with a line and we're done. Okay? All right. So now I want to talk a little bit about how do we understand how machine learning works. Okay? So this is a picture so this is kind of like the theory part of the talk. This is the picture that you would be taught in classes on machine learning or what signal processing, statistical inference. You'd say, well, we have error and we have model complexity. The more parameters I use in my model, the more I can fit to my training data. So that's what this training error is saying. If you give me a lot of knobs to turn, I can fit the data, the blue curve. But if I give you so many knobs that you really fit the data, you might not generalize too well. So the test error is saying how well will you then do on new examples that aren't in your training set. And the worry is that if you really kind of tweaked yourself so you get a really small error on your training data set, you might overfit. That's the overfitting problem. This is the overfitting picture. And so what you'd like to do is try to somehow figure out that sweet spot where you're getting kind of right in the middle there, where you don't have a lot of bias. So bias means your model's so simple it can't really predict anything, but you don't want high variance. That's saying that you're sort of so fitting and fine-tuning to the individual idiosyncratic nature of your data set, training data set, that it doesn't generalize well at all to new cases. Does that make sense to everybody? I think most people have probably seen some version of this picture. I pulled that off this web page. So here's that idea sort of graphically. I think this hopefully will work. So two-dimensional feature space. So the first thing you could do is say, let's try a line. So there's a line. That's the best line I could find here. It does pretty well. I guess it makes three mistakes. There's one red on that side and two blue on that side. I couldn't do any better in this particular case because it's not separable. So what you could do instead, though, is come in with some curvy line, or curve. I guess it's not a curvy line, it's a curve. Now I have 0 training error, so that's maybe good. But you could say, well, what would happen now if we got a bunch of new examples? There they are. So now here are a bunch of new examples. You say, well, wait a second, look at that. I did a lot of little excursions to get a couple of those blues and that red, but now when I get more examples, I'm starting to make a lot of mistakes on new examples with this. And maybe in hindsight, I should have just gone back to this line, and you'd say, well, yeah, that actually looks a lot better now that I see all those data, right? So that is the overfitting problem. This is the way we think about why that curve looks that way. This is the way it will happen if this is the way your data look. This is a real problem, and we understand how to deal with it. Okay, so how do we deal with it? Here's how we think about it mathematically. You have two things that you're looking at. You have your training error, E-train. That's what you can measure. You have your training set. It's got labels. You can fit your model to it and see how many mistakes it makes on your training data. That's something you can just compute. The thing we're really interested, though, is the E-test. That's the error on new examples that you don't have or you don't have labels for, right? You'd like to make sure that's small. And so this is sort of the fundamental theorem of machine learning. You just write this. You say E-test is equal to E-train plus E-test minus E-train. Nothing very complicated there for most of us, I think. What's the next step? Well, you say, well, we can do this. We can say, well, that's less than or equal to E-train plus some upper bound on that difference between E-test and E-train. That's the key thing. How do we get an upper bound? That's what a lot of math and statistics focuses on. And I'll just kind of tell you the rough rule of thumb is that that upper bound usually tells us something like that difference between the test and training error is going to be a function of the total number of weights or degrees of freedom in your model and the number of training examples you have, roughly like the square root of that ratio. So if you give yourself a lot of bells and whistles in your model, you're going to need more data to make sure that this is going to generalize well. Okay? So it's a pretty well-known thing. Yeah, I think people have seen it. Here's the picture again. 2 weights, I'll generalize well. 6, maybe I don't have enough data to really trust using 6-degree polynomial or whatever here. So here's what we know. And this is what we know and understand theoretically, empirically, very sound, really a driver in a lot of our work. We have N training examples. We want to design a linear classifier. What do those bounds mean? Well, it means that if I have D features, the test error is going to be less than or equal to the training error plus something that's like the square root of D over N. N is the number of training examples. D is the number of features I'm using. If we think that some subset of size K of the features are really relevant, and most of them aren't relevant. So for example, in fMRI, D, the number of features, is the number of voxels, maybe 10,000, but maybe we only think that a few hundred are relevant. K would be a few hundred, D would be a few thousand, so that's a big difference. But it turns out even without knowing which are the relevant features ahead of time, we can find them automatically from training data, and we have this kind of bound. E-test is less than or equal to E-train plus something that's like the square root of the number of relevant features only, plus a little log D factor. So it depends a little bit on the extrinsic dimension, all the features, but only weakly through that log. That's sort of the price we have to pay for searching for what are the relevant ones, divided by the number of samples. And then we can even do other things. We can say, well, maybe it's not even the dimension that matters. And it isn't always. It could just be the size of the weight. So here's another bound. E-test is less than or equal to E-train plus the square root, and that's just the norm or the square root of the sum of squares of all the weights divided by n. So there, the number of weights could be ginormous. As long as most of them aren't very big, it's going to be fine. It's going to generalize well. So why is this interesting? Well, this gives us great insight into how many training examples we need to learn. How many stimulus runs do I need to use with that patient in order to have any shot at figuring out what's going on in their brain with this machine learning thing? What we'd like to do is say how many labeled images do I need, just rough orders of magnitude, given my neural network and the job I'm trying to do. We don't know that. We don't know that yet. So that's sort of what I want to come to. So now let's talk about deep learning. So this is what's called the CFAR10 data set. It consists of 60,000 tiny little images, 32 by 32 in 10 different classes. Here are some examples of those 10 different classes. This is a test data set that people use. And here's an experiment that people ran. They took all these images. They trained a deep neural network, essentially the one I was showing you before, that Google one. And what they're showing here is accuracy, so how accurate. One is perfect accuracy. The upper curves are on the training set, so eventually they're just fitting the training data perfectly, perfect accuracy, and the test error is around 85, 86% there. So why is that interesting? Well, let's just look at it. So here is the inception network. It's got over 1 million parameters, about 1.6 million weights in it they're all learning. They're tuning those up based on only 60,000 examples. So remember before I said number of features or weights divided by number of examples. You had to have that less than 1. Well, this is way bigger than 1, right? We're hopeless. None of that stuff means anything. None of those bounds I showed you tell us anything about what's going on here. Yet it's still working. It's getting good test accuracy, state of the art. We can't do better than this. This is as good as it gets, okay? And so somehow, I'll just highlight those things there. What's the takeaway message? Overfitting works. That's the thing we're always told never do, never overfit. But guess what we're doing with deep neural networks? We're overfitting. In fact, sometimes we're not even just overfitting, we're actually interpolating the data. Remember polynomials and fitting polynomials to data? You can always interpolate n data points with a degree n polynomial. That's what these deep neural networks are doing. So why is it working? So here's the picture. I'm just going to show you. This is the sort of textbook story. Here's the deep learning story. I've just flipped that now. So now think of that vertical axis as error. So the training error goes to 0. The test error goes down to like 15% or so. That's great. So that part matches our theory, but this part doesn't at all, right? I have no bias and low variance. I'm getting everything. And it doesn't match what we understand to know at all. How? All I can tell you is this. There's something happening here. What it is ain't exactly clear. Probably some people are old enough to know that one. And that's a fact. Nobody knows. Nobody understands this picture. I mean, people try to make some attempts, but right now it's pretty much unsolved. Mathematically, just not understood at all. Okay, so here's one picture. Why might it happen? So here's a small training set. Here's the best linear classifier. Here's an overfitted nonlinear classifier. Will this work? Well, it would if this is what the rest of the data looked like. So maybe what's going on is somehow through these deep neural networks in a way that we don't really understand, it's sort of reorganizing our data into a picture that looks like this. So even though we pick out a few points and fit, intensively to that training set, it still generalizes well. And this goes back to things like k-means and nearest neighbor classifiers. So somehow, well, anyway, I'll just leave it there because I don't really know what I'm talking about, and I'm in good company because nobody does. But that's a picture to think about. Okay, I'll close just with a few quick things, open problems. So what are open problems and challenges? Here's one. Everything I just talked about, overfitting generalization. How many training samples are needed? Why do useful features emerge? Can we reverse engineer what that neural network is doing just so we can be confident that it's not going to screw up in some catastrophic way on a really important decision like a self-driving car? Will deep learning always succeed? What's going on? We just don't know. So that's why there's so much interest in this. Mainly we hear about all the amazing application successes, but you should really ask these questions because those successes, if we don't understand those questions, we don't know when it's going to break down. And that kind of gives me my next thing, robustness. Here's a great example of this where people trained deep neural networks to recognize street stuff, so you could have a self-driving car, and then some guy said, hey, if we just put some stickers on the stop signs, everything stops working for the deep neural network. Whereas, you and I would never be fooled by a couple of stickers on a stop sign. So these things are a little brittle. Why? What could be happening? Well, let's look at this picture again. Imagine that I just move that over there. So that's kind of one thing people are doing. They're saying take a trained neural network and just figure out how to just shift things a little bit, maybe in a visually imperceptible way that wouldn't fool us but fools the deep neural network because it's doing all this curving around. We don't really know yet, but that's a hypothesis. Here's another example. If you were driving down the street and you saw this, you'd probably slow down. You probably might even stop. You'd be like, wow, smiley face stop sign. What could that mean? It could mean that maybe kids are around or something. Who knows? But you would start coming up with all sorts of hypotheses. The machine would just blow through because it's not red. So we really do need to understand these systems, not for maybe routine things where we do have a human in the loop who can make sure that it's not doing something crazy. But if we're putting these into our infrastructure in ways that life and death matters, we have to be a little bit more serious about it. And then this is one thing, and I know this is probably super important in medical imaging applications, and sorry for the blurriness here, I'll just tell you what I'm trying to say here. This is the fact that ImageNet, remember, was this 14 million large data set of labeled images. That's great if we have 14 million labeled images. It took lots and lots of time to put that together. So a lot of the data sets we work with in other domains, we don't have such a huge labeled data set. So we'd either like to take a trained network from one domain, like cars and pedestrians, and transform it into something that maybe would be good for tanks and other military vehicles where we don't have so much labeled training data. Or maybe this is the idea I really like, which one of my friends, Greg, is working on. You want to train a deep neural network. Remember, really what we want the deep neural network to do is learn good visual features. Like the prediction thing is great too, but once we have good features, we can do whatever prediction we want. So what they do is they take color images, they decolor them, make a grayscale version of it, and then just train the deep neural network to automatically recolorize the images. So there's no human in the loop here. They just take, you have as many color images as you want on the web, take them, run a little algorithm to make them grayscale, then put the grayscale image at the input and say what I want at the output is the color image. It turns out that automatically the deep neural network can learn good features just from that sort of proxy task. So the ultimate task might be image segmentation or something, but they're using this other surrogate task which requires no human labeling to train the network and learn good features. Yeah.
Has anyone run that on a full black and white movie?
I don't know if they've done it on a movie. They've certainly, so they've done it on tons of still images. The features and representations they learn aren't maybe quite as good as the best that you could learn from the raw ImageNet data set of 14 million labeled images, but they're nearly as good, and it requires no effort from humans. So that's a really promising thing, I think, to keep in mind. And so then, just word of caution, if we're really successful, we might end up here. Don't want to scare you. Don't believe it myself, but VentureBeat does, I guess. But Elon Musk is also looking out for us. He won't let it happen. Don't worry. There's going to be no AI God. And I'll stop there and say thank you.
All right, any questions for Professor Nowak?
Yeah.
So, the example you mentioned about like full of many words.
Yeah.
So what if you use a linear classifier? Will it have a similar performance or?
So it's a little bit important that there are some nonlinearities in there. So the same phenomenon we see with deep neural networks, you can observe the same thing happening in kernel methods too, just regular kernel methods, like a Gaussian kernel-based support vector machine. If you run it in the same scenarios on the same sorts of data sets, like CFAR10, you actually see exactly the same behavior. So that's actually, I think, a very important direction for work. We don't really understand deep neural networks very well. We understand kernel methods a lot better, but still we don't understand the phenomenon I just showed you of overfitting there. So some people are trying to understand it there first in a more well-defined domain, kernel methods, and hopefully that'll give us insight there as well as the deep learning methods. So it's not just particular to deep learning. Good question. Yeah. Okay. So, yeah, so if you think about, I take one of those 32 by 32 images, I put it at the input, and at the output, I want to say a number between, probably what it is it's like there's a 10-dimensional vector at the output, And what you're trying to do is make the largest value in that vector appear in the right coordinate depending on what class that input image is. But basically just think of it as the output is a number between 1 and 10 saying what class that image belonged to. And then I'm doing that with these 60,000 images, and then I'm taking out from the whatever the current set of weights are. It predicts 2, but it should have been 3. So I back propagate an error signal, and it's just basically doing gradient descent on all of those weights simultaneously. We can do gradient descent officially. That's just back propagation. And we just keep doing that. We're just cycling over the data set. Every time we put in an input, we get out an output. It either agrees with what we want it to be or it doesn't. If it doesn't, we just back propagate that error and just tweak the weights a little bit all the way back through the network over and over and over again. And that's what those curves were, that over and over and over again. If I keep going, eventually it just fits the data. And what's really crazy is if you take the same data set and just randomly shuffle all the labels and train the neural network, it will perfectly train just on random labels, meaning the training error goes to 0 again. Of course, then the test error is horrendous because the labels aren't connected at all to the inputs. But somehow the capacity of these networks is such that they can fit arbitrary labeling assignments to these data. So they're very expressive. They can do a lot, which is also one of the reasons why it's so confusing that they actually are working. We don't know. It's really, not known by anybody. Laurent. Maybe Laurent knows. That you could fit all the data. But it is surprising that it would generalize well. Like the fact that you can fit randomly selected labels maybe isn't so surprising. Like you said, I have 1.5 million parameters to adjust. But the fact that if I train it with real labels on real data, somehow then on new held out cases, it's predicting super well, 85, 86% accuracy. That makes no sense. Or at least nobody has a good story that I've heard. Was there another question up here somewhere? Yeah.
So you said that the machines are not good as good learning as small humans, right? But is that really the case, or is it just that the children are seeing many, many, many cases and they're using pre-trained weights, basically?
Well, so first of all, a human, even a really smart one like Wally, cannot look at all these fMRI signals and figure out what's going on, right? So machines do have some advantages there. I think more to your point, though, think about the translation problem. I don't know, I mean, it depends, you have to ask Chomsky how much is baked in or not, but in terms of our language processing, a lot of it is learned, and humans can learn to translate between languages over, 10 years or whatever, and they're reading far fewer texts than we need to train these machines on. The machines are basically taking like UN transcripts, which no human could sit down and read in a lifetime, and that's what's being used. So that's why I mean, like, they're not learning as efficiently.
Also looking at things 10, 15 hours.
But how would looking at people and oranges and trees help me translate between Mandarin and English?
It may not, but it would help with recognition and those kind of
So I was sort of more thinking about the translation one, also the game playing one, right? I mean, I think that's another, we are general purpose machines. We do not have general purpose AI at all, none. It's pretty special purpose for the most part. And so, we're remarkable. And we're doing things differently than machines. So we should figure it out. Yeah. Maybe I think there and then I'll come down. Yeah?
You are implementing that overtraining is better. But in our application, I'm applying deep learning with layers in environment engineering field. And overtraining doesn't always give us good prediction.
That's, I believe it.
Is it only applied to imaging, or it depends on all different cases?
Yeah, so that's a great question. The question is, in this gentleman's experience, sometimes overfitting, overtraining of a neural network actually didn't work. It started to work worse. And so I think I wouldn't say that case study I just described is representative. It's just an example that we can't explain. It doesn't mean that you can, and I think that's what you say is great. I should have mentioned that sometimes we don't get that pretty story coming out. And so not only does it often not work the way I showed you, but we don't even understand how it is working when it does work. And so for all those reasons, we have to be very careful. And you can do a lot of experimentation, and you should keep doing it and using these things. But in the meantime, all of us, me and others, have to figure out why they're working and help you. Like, why is it not working in your case? Why did overtraining mess up? I don't know, and we should be able to help you with that. So we're working on it. It's a great question. Wally or somebody?
So yeah, sure. So a number of people in the med school have had a lot of success just trying really canned methods.
Yeah.
And then there's others who run into some problems.
Yeah.
So how do you see us in the med school like interacting with the Granger that you and your
Polling
professors
and
are
those guys,
bringing
yeah.
in to like how are you envisioning us interacting?
Well, I think on the one hand, like I said, I encourage you to keep trying those things out, right? I mean, if people weren't trying them and getting them to work, nobody like me would be, we got rid of neural networks. We banished them to hell because nobody understood what they were doing, and kernel methods were understandable. We had nice understanding of how many training samples we need, how robust they were. We understood everything. They worked well. They still work pretty well, but they don't work quite as well as deep neural networks. Although some of that might just be the fact that it's hard to scale up kernel methods to work on really, really large scale problems like 14 million images, because technically to run a kernel SVM, it would be like 14 million squared operations because of the way it's set up. So part of the success of deep learning was because they figured out ways to get these things to scale to really large data sets. So I think all I'm saying, I should just backpedal a little bit, keep experimenting, trying these things. But in terms of working with us too, I know that Diego and Poling and Varun, I think, are maybe considering like a 2020 proposal to try to start working together on this. So I do feel like it's going to take some teaming where maybe the end goal isn't to write necessarily the next paper for ISMRM or whatever it is, but to say, yeah, we want to keep doing those papers, but in the meantime, we're going to have this parallel track. We're going to try to do some things like this paper I was showing you, where they were showing like what's going on, what if we mess around with things a little bit, can we understand how fragile these things are. One of the things I like to do is take some medical imaging application and see how can we break it. Like once we have this trained neural network, it looks like it's working well, how robust is it? And that's where these adversarial kinds of examples come in. So I think it would be like teaming up on specific ways like that. And I think when it comes to medical imaging, where it's not maybe a life and death matter, or so sometimes it could be, I think there's a real good motivation to get this right in this kind of domain. And that's going to really require a stronger partnership. There's nothing like I can't come over and say, Wally, oh, you should just do this. It's just not that simple. I wish it was, but it's not anymore. And so we have to kind of work together. But case studies, working with real problems with real data, are key. So I think everybody on our side agrees with that.
We just had the organizing leader, Greg Kuchik of Stanford here, and he was saying the NIH is not funding a lot of machine learning because people claim to say, for instance, it's not mechanistic. But maybe the adversarial approach would be of interest to.
Yeah, I think so. Yeah. All right, why don't we take just one last question and then we just move this on outside.
Any last question?
I had a question about,
Sure.
about sample size.
Yeah.
And how to deal with the fact that in many of the cases we're exploring, we don't often have a large number of images.
Yeah.
Are there thoughts on how to best, or strategies, I guess, on how to best approach that problem?
Yeah, well, I'd be interested. I don't know if Rick's still here. Yeah, he is. In that segmentation problem, right? Just one segmented image gives you lots of examples of this is, nothing. This is patella or whatever. So I don't know how to actually count that. Like in segmentation, you're not just getting one label for the whole image like we were doing in this CFAR thing. You're getting, a few hundred labels because, of course, they're very correlated. They're not like 100 independent examples. So it's a little hard to judge exactly how many data you need. I don't know, Rick, do you recall how many segmented images you guys need to give as training data for these? Yeah. Yeah. And then you have a lot of, again, individual pixels. Each of those is a prediction, right? Each pixel that's in one segmentation set or another is a prediction. So that 30 odd images, maybe it gives you a few thousand examples of some sort. And then also I think they did a very nice design of their neural network so that it was capable of doing some pretty great stuff, but not like, you know, so unwieldy that they needed tons of data. So that's, again, where there's some engineering expertise that comes in. Yeah, but I don't know. Like, would we have known that about 30 would be enough? Probably not, right? You did 30. It seemed to be working. So, but if it wasn't, maybe you would have gone back and got 100 or more and see if you could get it to work then. So, I mean, that's certainly totally reasonable way to do it. But I wouldn't have, I don't know if anybody in this room could have guessed how many you would have needed ahead of time.
Do the statistical approaches that were framed around other classifier approaches, like leave one out, for example, or something like that, do those apply here as well?
Sorry, could you just mean?
So, for example, you can train on N minus
Yeah.
1 samples
Yeah.
and then test on the N.
Aha, yeah, okay, yeah, I should have actually, since that's probably a very common way people look at things, you can actually write down, you know how I had those bounds, test error less than or equal to training error plus something. That plus something could be a cross-validation estimate of the holdout error too, and there's ways in theory to support that. Usually to get, you know, theoretically sound kind of bounds, you do more than one holdout. You would have to hold out a kind of larger subset, but that's technical. So yeah, you can use that. And but again, in terms of a deep neural network, it's not clear exactly how to interpret any of these things there. Yeah, I mean, but certainly that's what I would do. You should never not do cross-validation. And if cross-validation is working, then that's a pretty good, a reasonable way to get a sense of how your test error is going to look, right? There's nothing wrong with that. I mean, that you can do with any black box. You can give me any function f that is a predictor, and I can run cross-validation, and that cross-validation error does tell me something about the generalization error. There's nothing complicated about that. I should add that slide to this talk because that's a great point. I'm glad you brought it up.
Having comments about data size. So we tested with various number of data samples, and you know you have to find some optimum data set. Otherwise, you know, if you put infinity numbers, that doesn't mean that you will get a better prediction. And in our case, sometimes we get 300 gigs a day of data, and we have to feed it into your system.
Wow.
So it's very difficult.
Wow, yeah. All right. Well, please thank me or join me in thanking Professor Nowak.